I think a few of you know me from some various presentations over time. Here's a little bit about me. I am a security analyst and researcher at Black Hills Information Security. I do craft malware, helping out the pen test operators and the red teamers here at Black Hills. I'm also an instructor for the Antisyphon Training courses. And if you are interested in what we do at Antisyphon, you can also always visit antisyphontraining.com. I have a couple of free courses with Antisyphon, Enterprise Attacker Emulation and C2 Implant Development, which is kind of a edgy malware dev kind of class. I'm getting ready to actually revise that one. I also have Regular Expressions, Your New Lifestyle. If you're interested in regular expressions, that's a very helpful learning experience. And my new class, which I just brought out this year, called Introduction to Python. All right, so here's the scenario. You're performing an internal pen test. You find a system with a really old version of some SNMP manager software, and you're like, this thing might be buggy. This thing could have a problem. So you run out to Exploit DB, which is a community resource that's been around for a long time where people post software vulnerabilities along with proof of concept exploits. And you search for this thing and you get a hit, right? Bingo. Sure enough, this software that you've discovered happens to be vulnerable, okay? So that's the scenario that I've painted. What's the real story? Well, I was looking for a topic for this week's webcast, and I went out and searched Exploit DB and picked a vulnerable app from the various exploits that were published and found a Python proof of concept script for that vulnerability of this app to present about. And then I'm going to talk about my journey that I've had this week with this vulnerability and the Python proof of concept script that came along with it. So hack like it's 2010. Well, sort of. The vulnerability I found was a piece of software called Maple Computer WBT SNMP Administrator, a particular version with a remote buffer overflow. Wow. Well, it's almost like hack like it's the 1990s. You don't often find a remote network socket-oriented buffer overflow in software these days, mostly because a lot of the technology and compilers, modern compilers and languages have improved to the point where it's not often something that you will discover. But they are still around in places, and it's usually older applications. And in this case, it's a 32-bit application, and that's actually kind of important for this exploit, of a particular SNMP manager piece of software that had not only the exploit proof of concept itself published on Exploit DB, but also had the related CVE and the vulnerable application itself. The exploit itself is written in Python 2. One of the things that you should know about Exploit DB is your mileage is going to vary a lot. Some of the things that you find on Exploit DB are professional grade, wonderful exploits. Some of them are direct contributions to things like the Metasploit framework, for example. And other things that you find on Exploit DB might even just be a text description of how to exploit something. Or you might find something like a C or a C# or a C++ or a Python or a Ruby exploit that is relatively functional. It's going to be kind of all over the map, right? Anyway, for this particular one, after downloading the exploit, well, you're a little sad. And the reason you're a little sad is you find out very quickly that it's written in Python 2. It seems out of date. Your Python knowledge is a bit lacking, but the version seems to match of the software, and the exploit DB actually does contain a copy of the app. So why don't we try it out, right? And see if the software truly is vulnerable. Let's see if this proof of concept actually works. So some details about the software and the exploit itself. Well, this thing called SNMP ADM.exe, it's got an unauthenticated remote buffer overflow via a long string to this CE remote feature, which is listening on TCP port 987. And the author of the exploit, these are his words here, claims that we're able to overwrite data on the stack, subsequently get some of that data into the CPU registers that allows us to control the program execution flow, resulting in the attacker-supplied remote code execution ability. Furthermore, authentication is not required for this exploit to succeed. So I would say this is a dangerous kind of exploit when you come across this sort of thing, okay? No authentication, listening network socket, remotely exploitable, just have to be able to craft the right payload to send to it. Now, if you read further down in the exploit text itself, you learn that there's a particular opcode sequence call EBX that we can use to act as a bit of a trampoline in this exploit. If we can manage to load EBX with our own value from stack abuse, as in the input that we supply, it looks like we'll be able to use call EBX to our advantage as a trampoline. We not only have to get this right, we have to also control where the execution is going to land when we use this trampoline to exploit this. So you pull down the exploit code, and the first thing that I did was, okay, let me look at this inside of a text editor, and I use VI because there is no other editor but VI for somebody that is old school trained since about the early 90s on VI or ed or sed. Like, I'm a UNIX bigot. I admit it from a long time ago. VI rocks, VI improved rocks even more. So I look at it in VI. If this is VI improved, there's a little bit of color highlighting. It is inside of PowerShell. And as I look at the script, I see a few things here. I see a couple of statements towards the top of the script. EIP equals struct.pack. I'm like, well, what is struct.pack? What is that, right? Pop EBX or Pope BX? Pope BX? No, that's probably Pop EBX, meaning they're pointing at a couple of opcodes inside of some memory location. It's also got struct.pack. I'm like, okay, cool. And then I look down a little further and I can see, this buff0 here with some number of letters multiplied by some large number, 693,704, or 692,292. You can see in here I'm actually editing and I'm working on it a little bit as I look at the exploit. And then I see buff1 and buff2, and I see inside of Python where the payload is kind of the concatenation of these three buffer elements. Like, okay, so I'm getting a little bit of a feel of what they're trying to do with this remote exploit, right? There's a lot of padding in front of then a particular instruction that is passed in this EIP variable, followed by another pop EBX buffer of 4 bytes, then the shell code, and then some more padding on the end, essentially. All right, cool. Well, that's good. We do need to know how things work a little bit, though. I also see in the code this thing that with a def statement called do it, and what looks like network connection sort of code to me, right? Now, I do know Python. I'll explain it a little bit more. And then I see a little bit of miscellaneous other stuff around parsing the arguments and actually launching the script, all right? But we kind of need to know how these things work. What is struct.pack? How does the Python socket module work? What is this Argparse thing? What is this test for this double underscore name variable in here, right? So let's go forward, right? So the next thing I did is pop up my handy Windows 10 virtual machine. I just cloned one of the Win 10 machines that I have for research purposes, and I installed the latest Python 3 on that Win 10 machine. And then I took the software itself and I just ran it on the machine to see if the software would actually run. And this is the so-called vulnerable software, right? And I get this window up asking for initially a login, and I just click OK on the login without even entering a password, and I get this SNMP administrator window up. So it appears like the software runs. It appears like the software looks more or less stable in this first instance, okay? So I grabbed the proof of concept and I'm like, well, let's see if I can run it. And I run it with python.exe after installing Python 3, and I very quickly discover that the proof of concept appears to be written in Python 2. Now, one of the really big telltale signs of that is the print function in Python 2 is actually a keyword that is built into the interpreter. So it's just print space and then some quoted string. Well, that's not actually a legal statement in Python 3. And so, frowny face. This is not going to actually work. We need to first consider porting this script or converting the script to Python 3. Now, that's one choice, right? The alternative choice is to go back to the Python website, find a Python 2 interpreter, install it, and run the actual proof of concept exploit in Python 2. Either way, you can do this, but I'm a big fan of Python 3 because we should all move into the modern world. So I thought, why not take the opportunity with this particular exploit to go ahead and port it over to Python 3. So this happens to be an additional tool that's available with Python 3. That's actually a conversion tool. It's called 2 to 3. And this thing is in the form of a Python package that you can install using pip, which is the Python, really the de facto community Python third-party package manager these days. Pip was not originally shipped with Python, but now more and more you find it on systems and you find people installing it anyway because it is the community third-party package manager of choice, right? So we go out using pip and we install 2 to 3, and then we attempt to perform the script conversion of the proof of concept. And 2 to 3 has a flag called -w that will overwrite the original script that you provide as input for 2 to 3 with the modified script. So before you do this to your original script, it's probably a good idea just to make a copy of it. And that's what I did. I copied it to another file called exploit3.py, and then I ran it through 2 to 3. And 2 to 3 will show you some diffs in diff language world, if you like, that show you what it is changing, right? You see minus next to these two prints, and then plus as it puts parentheses around the prints to modify them to being Python 3 syntax, right? And in fact, largely with this script, seeing as it's a fairly small sample, that's about all that occurs is the print statements are actually replaced. All right, that's cool. So let's go ahead and try it again, right? So we hit it again with python.exe /exploit3.py, which is my refactored script at this point, and we run into more trouble. I was like, oh man, what are we going to do now? Okay, this is a challenge. Well, being somebody that's written code in Python for a long time, I happen to know that one of the fundamental differences between Python 2 and Python 3 is that the string object in Python 2 has changed to a new representation in Python 3. In the case of Python 2, the string object was simply a series of bytes. The string object essentially could only hold ASCII characters. They could only be 8 bits maximum. In Python 3, the string object has now been changed over to being UTF-8 encoded. And UTF-8 happens to be a variable length encoding, which allows you to encode up to 4 bytes as a single character so that it can represent the entire Unicode set and different languages and things that go way beyond ASCII, right? So when we tried to run this exploit, we end up with a problem that we cannot concatenate string and byte objects. So when Python 3 introduced UTF-8 for string objects, it also introduced another object, which it calls a byte object. And the byte objects are actually compatible with what are formerly known as Python 2 string objects, right? The bottom line here, in order to make this exploit work, we need all of these different buffer elements we're trying to put together into our payload to actually be byte objects. So we have to manually edit our script now to turn the various elements in here into byte objects. Well, you can see there are multiple things here. Now, the first element that we see in the proof of concept script is actually the shellcode. And the shellcode is a short shellcode that is written to pop calc.exe on Windows 7 SP1. That's also a hint for later, by the way. I'll hold that thought. And the shellcode in the Python script is represented as hexadecimal escaped characters. So \x31, for example, is the hexadecimal character 31. \x F6 is the hexadecimal character F6, et cetera, et cetera. In Python, if you want to represent a string object as a byte object, you can place a lowercase b in front of that string object. And so if we add that little lowercase b in front of all these quoted strings in the script, they become byte objects. So you can see that I've highlighted all those places here with the shellcode itself, and then down here with these individual characters that are multiplied by some number. Now, I didn't have to do it for the struct.pack stuff because, as we'll see in a minute, the struct.pack returns byte objects already. So the act of doing this alone has now brought our script to a functional status, right? A couple of other things to point out. When you have a single Python character like quoted B here, and then you multiply it by a number, 693,704, for example, what you're doing is just creating one giant long object that is 693,704 of the letter B as a byte object. That's our padding that we're going to push in at the front of this buffer overflow so that we can then exploit the stack and place our EIP in the correct place on the stack, and then subsequently our popEBX pointer as well as the shellcode, and then some extra padding on the end. For some unknown reason, that was required. Probably the author was searching using the R and the W as kind of Easter eggs to search for where in the memory his exploit was landing, because you kind of, if you sandwich it between two things, like a ton of letter B's and then a ton of letter R's or W's, you can actually see where your code lands as you're scanning through memory. Okay. So given that, we're close to a functional exploit, we think, and we can run it in Python 3 just to have Python check the syntax, and we're going to see that the script appears to run. And when we look at the help, we're going to see that we have to supply an IP address for this exploit, which will target the reported CVE 2019-13577. But wait, we need to understand a little bit more. What about that struct.pack stuff in our Python script? Okay, so we have two lines in the script that assign the result of a struct.pack operation to two separate variables in this case. Well, what struct.pack does is it converts between Python values, and in this case, they're Python integers expressed as hexadecimal, and C structures represented as byte objects. So when we perform this struct pack of this integer 0x1008fb3, we are taking that 4-byte integer and packing it into a buffer. And that buffer becomes a byte object representation of that integer. Now, great, but what does this L and what does this less than symbol mean in that first parameter to struct.pack? Well, these are components of struct format strings. And the L in particular means we're going to pack an unsigned long integer, which by definition is 4 bytes long, into this byte object buffer. And well, that's what we wanted to do, because if we think about an address in a 32-bit machine representation, that is a 4-byte entity that we want to pack into this buffer. Well, what about this less than greater than thing? Well, this part of the packing operation is about the order of the bytes as they are packed into the buffer. If we use the character just at, it will be native order of the processor that it's running on. That would be little endian on Intel CPUs. If we use equals, it means the same thing. Or we can explicitly use less than or greater than to be little endian or big endian, depending on what byte order we are searching for. And then there's also an exclamation point, which is really just an alias for big endian. It means network byte order, and network byte order has always been defined as big endian. What does this endian thing mean? No, it's not Indian, it's endian. Endian. It means which end does the byte sequence start? And this is a byte sequence. It has to be 2 or more bytes, right? Order of bytes, not order of bits, order of bytes, all right? So keep that in mind. A picture is often worth 1,000 words, or we can demonstrate inside the Python interpreter itself, right? So let's say, in fact, I'll bring it up on a slide here. Here's a Python interpreter. If we wanted to represent an address in memory, we could do something like this. And we can look at that. Actually, sorry, I should make that a byte object, not a string object. But specifically, we could look at that in the interpreter, and we can see that, yes, we have a byte object with hexadecimal 00, 01, 02, and 03 in it. But when that's interpreted by the CPU, it's going to be interpreted as little endian, right? Well, little endian means that the least significant digit there is going to come first, the digit on the other end, if you like, or the hexadecimal character on the other end. Well, let's demonstrate that by using pack, and we'll do little endian L, which is a 4-byte integer, and do 00, 01, 02, 03. It's the same 4-byte integer, but I want you to notice that the byte order is 3210 instead of 0123. Whereas if we did greater than L, big endian, the byte order is in the same order as the integer that we supplied, 0123, right?
So, Joff, I want to jump in real quick because there are 2 questions in the Q&A that I don't want to save till the end because they're very specific to what you're looking at here. We have one question here. How was the string converted to bytes for the exploit to work? And they said, sorry, I missed that.
Okay. Yeah. So the question, how was the string converted to bytes for the exploit to work? All right. Well, there's 2 parts of that. One part of that is the string itself, right? So you might have some machine code that looks like this. by the way, the opcode CC is a break in Intel opcode. So if it encounters CC, that means stop the instructor, stop the CPU immediately. Is it C3 or CC or C3? Actually, it might be C3. But anyway, the question is, how was this converted into byte objects to begin with? Well, it really is this simple. We put a little b in front of it, and then we look at the type of the object. And this is now considered a byte object, class bytes. Whereas if we had defined the shellcode as this without the little b, it's class string, right? And if we were to encode that to bytes, you can see that that string, CCCC, actually turns into a whole lot more bytes than we think it would. And that's because of UTF-8 encoding. Right, so we need to work in native bytes is the bottom line here.
I think you answered the second question. How do you print the exploit as raw bytes without having B on your way? Something like junk plus exploit instead of B junk plus exploit. And I think you just explained that.
Yeah, I think I did too.
Okay, right. Very good. Thank you.
All right, so let's go forward. There's a second component here which relates to the question that Ian was just asking. And the audience member was asking. Thank you, Ian, for passing that along. And that is the socket module, okay? Yes, we can define this exploit inside of the script, but the next job that we have is we have to transmit this data, this blob of bytes, right, to the actual TCP port 987 of the listening application. And this is where we need to use the Python socket module. Inside of the code, if we zoom in on the doit function, we can see that there are 3 lines of code here underneath that try statement. And that is socket, followed by connect, followed by send. And these are 3 function calls out of the Python socket module. The first one, socket, establishes a socket handle. The second one actually performs the TCP connection to the destination IP and port. And the third one actually transmits that byte object payload to the target, okay? And the rest is really just fluff, right? Then we close. I'll talk about a little bit about the exception handling in here in just a moment. So the Python socket module has this function call called socket, where you have to provide it an address family and then a type of a socket at minimum. The address family IF_INET means IPv4. If you have a socket type, sock_stream, that means TCP communications, right? There's also something called sock_dgram, which is analogous for UDP communications. But we know this thing is listening on a TCP port, so we need sock stream. Socket.connect, as we said before, simply connects to the remote socket at that address, and then socket.send will send the data in a byte object that you supply to the remote IP and the address. Now, there's a related concept here, and that is, how come we were just able to use socket inside this script instead of socket.socket, which the module examples show? The reason we were able to do this is the script author for this proof of concept decided to import all of the socket module attributes and functions into the script as global namespace items. This is the from socket import star line at the very beginning of the script. Now, this, in fact, is not a best practice. Typically, you would just import the entire socket module into its own namespace, which would be called socket, and then you would use socket.socket instead of just socket parentheses and so forth, right? However, that's how this particular author chose to do it. Right? The connect function call requires us to provide it a Python tuple representing the address. Now, a tuple is simply a collection of objects. In this case, we have a string object containing the IP destination address we're connecting to, and then an integer object containing the TCP port number of 987. And then, of course, as we said before, the send call will simply send the bytes of the payload to that destination socket. What happens if we cannot connect? This is where the exception comes in. So you'll notice that we have the socket connect and the send method calls all in this inside of what's called a try block. So we are effectively and quite intuitively from a Python and English language perspective, trying to make these function calls. If we fail, then an exception will be thrown in the Python interpreter, and the exception will indicate that we were not able to connect for whatever reason. It could be that the socket refused the connection, or perhaps there was a timeout, or perhaps even we have an IP reachability kind of issue. But either way, we will raise an exception in Python, and if we use the syntax accept exception as E, as written here, it catches a generic exception, allowing you to print that to screen or do whatever with it you're going to do, right? So I'm just kind of breaking down the components of the exploit here, right? So what's the overall flow? Well, we import the required Python modules. We define the global variables, which include constructing the payload, as we saw before. We've got three functions here: do it, parse, args, and main. Do it is the actual exploit itself. And then at the bottom of the script, we're testing if we're running as a script or a module and starting the main function to perform the requisite actions, assuming we're running as a script, which we will be running as a script. Now, what about the payload itself? Let's zoom in on this just a minute. So we have 693,704 of letter B in the default payload. That's a whole bunch of padding. Then we have the memory address 1008FB3 packed into a variable called struct.pack. That's the very next thing that's going to be in that buffer when you look at that buff2 statement there, second from the bottom in that black box up there, right? Then we have the address 0x022C0012, also packed into a variable called popebx. Now, when I analyze the exploit, at that particular address, when you disassemble it, should be the opcodes popebx, which is actually just a single opcode, 0x5b. Then we have the shellcode itself, and then we have some other padding at the other end of the exploit, right? And that's all concatenated together as one big byte object in our Python script. As near as I can tell, as I analyze the flow of the exploit, it works like this. The padding is what's used to overflow the input buffer listening on port 987. The overflow actually occurs right after 106,012 bytes, way earlier than the amount of padding that was supplied. However, having said that, the extra padding is needed so that we can keep walking down memory to eventually overflow that first structured exception handler pointer. And that's what we're really going after here, okay? So we get enough bytes to travel down the stack and overwrite that first SEH pointer with the address 0x10008FB3. I think I added an extra zero there, sorry, right? Then right after that, we write in the value 0x22C0012, and the code earlier in the actual application itself will have had a move EBX from a pointer to bring that into memory. So that value will end up in the EBX CPU register. Then, as we exploit this, the app throws an exception, most likely due to a corrupt stack return address or a stack canary pointer, although I do not think this was compiled with any stack protections. So probably the return address. The instruction pointer goes to 0x1008FB3, which in turn executes a call EBX instruction. EBX is already preloaded with the 0x22C0012 address so that the instruction pointer is transferred to that address, and then EBX is popped, very first opcode at that address, and then execution continues on into the shellcode. And that's how the exploit actually succeeds, if everything is perfectly normal. One quick digression, you might have saw the Argparse module in the exploit. In short and quick terms, Argparse just allows us to provide the command line argument of -I so that we can supply that IP address parameter into the script when we run it. So argument parsing in Python, this is just a standardized way of doing command line parsing. And it's really helpful because actually writing code in Python to parse command line arguments would be kind of a difficult and arduous task, right? All right, so we're ready. Everybody, we're ready to actually exploit it at this point. So I use my Windows 10 system. I fire up this SNMP application. I run the exploit pointing to address 127.0.0.1. And immediately the application pops up, exception, access violation in module SNMP ADM.exe at 1db92. And it's an accessation violation for the address 41db92, trying to read 42.42.42. Well, that's cool. If you think about the hexadecimal character 42, that is the letter B. So this thing threw an exception because it was trying to read an address of 42.42.42.42. So clearly, we have been able to overwrite a CPU register with this attempt. We don't know which one. We haven't put this into a debugger or anything like that, but we definitely have a denial of service. Right? There's absolutely no doubt of this. All right, cool. So we're partially there. So we're feeling pretty good about ourselves. If we want to go further, we have to roll up our sleeves beyond our Python programming skills and enter the world of code debugging.
Thanks for watching. Don't miss part 2 of this series coming up next.